story that happened last year. We have a colleague here from Lie algebras called Raimundo, who started to realize that the groups in IMPA were not very well established and well written, was a bit fuzzy. And then he wanted to catalog everything. He started asking everyone, what do you work with, what do you work with? And he realized that 90% of the people at IMPA work on mathematical physics. I mean, yeah, I work on mathematical physics. People who work on Lie algebras work on mathematical physics. Symplectic geometry is mathematical physics. And yeah, he realized that you have to squeeze a bit more out of the people, or you have to accept that people work on related things, although it doesn't look like. And there is another fuzzy boundary here at IMPA, which is if you ask me a bit more what I work on, I say, okay, it's math physics, but it's more like porous media. And of course, there's a whole group here that will answer the same question. If we look at the papers themselves and the talks, there's still a lot to learn to understand why both call this porous media. And I don't intend and I don't feel comfortable in bridging this gap. So what I'll do is much less ambitious. I'll just present what I do. And hopefully, I think this conference will be very fruitful for us to understand what are the links between these two. So this is joint work with Daniel Alberg, who's back there, and Vincent Tassion from ETH. So it's a model of porous media. So we start with, it's a very hands-on approach. So we take R2, and we define what the random media is. It's for us, probably it's a porous media, just a random media. And we define exactly where the particles are, where the impurities of the medium are. And we try to study it from a statical perspective, not dynamic so much. So we start with a Poisson point process in Z2, in R2. So let us denote this by xi. And it has a density, which we call lambda. So fix some lambda, say, between 0 and infinity, and you put these points in the plane at random according to the Poisson distribution, which is the most uniform way you could do it in using independence. And for each of these points, we are going to assign a radius. So let Zi be random radii. So they are independent and distributed according to some distribution rho. So you have some distribution on R plus, which gives the random radii, and we sample independently for each point with random radius, and we draw balls around each point. So let's just introduce one more notation. O will be the set of all the balls, the union of all the balls with centers xi and radius zi, while V, so this will be the occupied set, the set occupied by balls, and V will be just the complement, R2 minus what's left vacant in the plane. So why these two definitions? Because depending on the interpretation you have for the balls, you could think that balls are, say, obstacles that don't allow the fluid to flow. And in this case, we'll be talking about percolation on the vacant set. Or you could think of the balls as, say, some conductive, electricity conductive blob. And then you would be talking about conductivity in the occupied set. So interested in both. Most of the work up to now has been focused on the occupied set, but for practical reasons. It's usually easier to analyzed in the vacant set. So those are some Blackboard simulations of the process. And I'll come back to those 4 scenarios later. Oh, yeah, it's one of them is impossible, so you tricked me. And by the way, you could think of which of these are impossible for now. So what types of questions are we interested in this random media? So we are mainly interested in statical properties of connectivity. So is point X connected to point Y through either the vacant or the occupied set? Or we could also be interested, so we denote this event by this. We can put occupied here to emphasize, or vacant. But we'll also be interested by the possibility that X is connected to infinity by either the occupied or the vacant set. By this we mean there is an unbounded continuous path that stays the whole time in the occupied set and starts at X. And we are interested in the probability of such an event. Yes. It will, I mean, unless in the very trivial case that I'll explain later, it will have infinitely many connected components, but there is a very beautiful argument showing that it can be at most one unbounded one. So unbounded components are only one. So it's impossible for 2 unbounded components to live in peace together. They will merge or they'll die. They have to choose. So, and since we are probabilists, we want to understand the probability of such events. So by translation invariant, we will forget X, but always 0 here. So the probability that X is connected to infinity, that's a very interesting quantity, either for the occupied or vacant set. And the probability that 0 is connected to some point X far away is also interesting. This converges to this as X goes to infinity by some trivial argument. So, yeah, thank you. This converts to the square of this, and yeah, we are mainly interested if this is positive or 0. So if this converts to 0, this is 0, the square doesn't change anything. So why this converts to the square of this? Because essentially 0 has to be connected far away, and X also has to be connected far away. So I have 2 local components adding to this. And the 2 main definitions that we are going to define, that are the last definitions, I promise, are the critical density lambda. Lambda C is the supremum over all lambdas, such that this probability is 0. I'll explain more in a minute. And the same for the vacant. So essentially, as you increase lambda, you are putting more and more balls into the picture. You're increasing the set O. So you expect that at some point, there will be a positive chance for 0 to be connected to infinity. And at the same time, you're decreasing the vacant set. So you expect that after some density, there will be no chance anymore for the vacant set to be connected to infinity. So if it takes some time because there's an infimum of probability 0, but there is a picture that helps more than the definition, I think, which are the 2 possible scenarios. So there are the trivial scenarios. This could be 0 or infinity, or this could be 0 or infinity. And then, it's basically one phase all over the line. I'll explain this later. But there are the 2 interesting possibilities that lambda C is smaller than lambda C star, that lambda C star is smaller than lambda C, and that they're both the same. And of course, they could be trivially equal to infinity, trivially equal to 0. So what happens in this scenario? You have to think a little bit, but if you are here, you are below both. So there is no infinite component for the occupied, the too few balls to connect to infinity in the occupied set, but enough space to connect to infinity through the vacant. So this is simulation A, this picture. So you can connect to infinity through the vacant set, but you cannot connect through the occupied. Here, you kind of in the opposite regime, where you can connect to infinity through the occupied, but not through the vacant. And here it's something strange happening. You are above this supremum, so this definitely is positive. You have a positive chance to connect to infinity through the occupied. You are below this infimum, so this should also be positive. So there's a positive chance that you connect in the vacant. So somehow the vacant and the infinite and the occupied unbounded components are living together. This is this picture here. There could be an infinite occupied guy and an infinite vacant guy. This is not a ball in the process. Living together. And they have to kind of spiral somehow. It's very strange. So this is strange. That could happen. So this is D. Here is also AB. Here is also AB. But here the opposite is happening. There is no infinite component either in the vacant or in the occupied. So this is C. You see, you cannot go to infinity through the occupied because there are circuits, vacant circuits surrounding the origin. You cannot go to the infinity through the vacant because there are infinitely many occupied circles surrounding the origin. So in fact, this picture, you should really think there are infinitely many vacant and occupied circuits surrounding the origin. Otherwise, we are not in C. If there are only finitely many of them, you could escape at some point. So this is also very strange. Could this too happen? So that's the question of sharpness. Can we show that essentially we are in this regime, where lambda C equals lambda C star? It's the most intuitive from the physics point of view. These somehow are not only strange, but very unstable situations. So first, result in this direction. So first, there is an important observation. No, let's go to the result first. It's by Roy, who worked a lot on this subject. So he considers the case where rho has compact support. So there are no balls larger than, say, 10. Then he showed that, in fact, the critical values are non-trivial and they're equal. So trivial, I mean, if both were 0, we would have B all across the line. If both were infinity, you have A all across the line. So they're both non-trivial and equal. You're in this situation star here. And more than that, you have subcritical and supercritical results. If you are below the critical value, then you should not be able to connect to infinity by the occupied set. But even connecting to some fixed point has an exponential cost. So the probability that you are able to travel far away is very small, exponentially small.
In the simplified case, instead of R2 is the line. The phi1 is clear, but you can go over infinity.
Sorry?
You're in the trivial situation, but you're in the real line.
Yes.
The same process of the real line.
No, the real line is just for the parameter density.
But the equation is the same process,
Oh, yeah.
but on the real line instead of R2.
Yeah, then,
It's obvious that the occupied ones always escape infinity.
no, it depends on in this scenario here, where rho has compact support, it's clear that you're going to find infinitely many balls in the interval to your left and right, so you cannot go in the vacant. And it's also by the ergodic theorem, there will be some vacant regions around the line, so you'll also be blocked to find the path in the occupied. So In the one-dimensional case, you cannot go because you cannot go around problems.
No, but at least one. So it was like just from the 2 pi. There's always, so the equation is from the 2 pi ones. Okay, but no, the one that's the poles.
Yes.
So there is always a lambda that you always can go to infinity.
No. For every lambda, if you take the density ridiculously high, you can always find some hole somewhere to your right and to your left, so you're blocked. By the ergodic theorem, the density of holes and the density of occupied should converge to some proportion, and it means there are infinitely many vacant points and occupied points to your left and right. But this is for bounded support. I'll explain soon what happens if you take unbounded support. Then the balls could be so big they breach the gap. And on the other hand, if lambda is bigger than lambda c, the same happens for the vacant. The vacant is dead now, cannot be connected to infinity, but actually cannot even go very far. And this is the general picture everyone expects, because not only holds for bounded support, but holds for other random media models, like Bernoulli percolation, which is another. It's a discrete counterpart to this. So why are these two facts important? I mean, these quantitative bounds actually help prove other results about the model. We are asking some very trivial questions about being connected to infinity here. But if you have these quantitative bounds, you can even try to understand more detailed aspects of the problem. For example, how a Brownian motion behave here if it bounces on the balls. You will drop it in the infinite cluster. Does it satisfy something similar to the heat equation? So you can ask dynamical questions once you have these quantitative bounds. Otherwise, it's just knowing that you have an infinite cluster to navigate on. It's too little information to go on asking further questions. For example, what's the total flow you can send from the left to the right of a box? It's a very quantitative question that needs this type of estimates, for example. So this talk is about unbounded rows. So what happens as you drop the assumption that they have compact support? One very important observation is that if rho does not have second moment in this sense, then the balls have infinite expected area. So the area of a single ball is infinite, in expectation is infinite. And this implies, Hall observed this in quite a big degree of generality, this implies that the occupied set will be the whole plane with probability 1, almost surely. So, you just have to see if one point is covered or not. Is the origin covered with probability 1? Maybe not by the points around it, but as you go far, the probability that someone covers the ball starts to increase because you have more area to look for the center, and the decay of the probability that someone goes that far, from that far to the origin, doesn't decay fast enough to compensate. Yes?
Yes, it seems to be the most important assumption. So somehow you can work with a rho which is not a probability, right? You can work with a measure that has infinite mass and look at the Poisson process with consensus lambda.
Yeah, if the mass starts to blow up the origin, you have other types of problems. Like if you have, he's asking, like, you could put infinitely many points as soon as the radius starts to become very, very small. And it can be done, and you can even get some nice models that have some scale property. You shrink the model, you get the change in density. But yeah, it's...
So it changes qualitatively the behavior of this probability.
These already changed. I mean, even what I'm considering, where rho is a probability, already changed qualitatively the behavior. So that's the second observation. That's observation number one, that you should assume at least this. So we assume from now on that the integral of z squared, the rho, is finite. Otherwise, we cover everything. And this is also true for the line. If you assume that the integral of z, the rho, is finite, in the line you cover everything. Now the second observation, and I have still 10 more minutes, right? The second observation tells us that, we should be a bit more careful because at least one of these guys is not going to be true. So what's the probability that the origin is connected to X through the occupied set? Of course, you'll not be able to calculate this. It's too complex, but you can give low bounds. This is at least the probability, that one ball connects the origin to X. If one single ball touches the origin and touches X, this happened. And you can bound this by, the area. You take the origin here. You take all points. So this is X. You take all points that lie in the ball of center origin and twice the radius. This is twice the radius. So there is an area proportional to the radius square. And then you have to pay for someone here in this annulus to appear and cover both points. So if they have radius, say, 4 times this, they cover both points. So, okay, you don't have to really be picky about this estimate, but I'm just saying that if rho, in the previous case it was fine because rho had compact support. But if rho has slow decay, say polynomial decay, which satisfies second moment, but say if this, the probability that to have a ball of radius, that one given radius is bigger than this, decays like, say, this, which is perfectly fine. It's very fast decay. You don't get an exponential decay for this event. You get a polynomial decay. So this is going to be hopeless for the unbounded case. And this also shows that the methods have to change a little bit. Because the methods developed by Roy either give you everything or nothing. Either they give you the exponential decay or they don't give you anything. So I think it's time to write down the main theorem. So this is by Daniel, Vincent, and myself. And by no means this is not a sponsored talk. So first result, so under the minimal assumption you can hope for, which is finite second moment. So this is 2 papers. The second one is to appear. Under the minimal assumption, lambda c equals lambda c star. So there is one only phase transition where this happens, where connectivity changes. If you have lambda smaller than lambda c, so you are in the regime where the vacant percolates, not the occupied, then this probability should go to 0, definitely. And it goes to 0. I'll not write it down, but the rate that it goes to 0 is more or less this, essentially this. So essentially what you can hope for. There's some correction, but essentially what is expected. So what's the moral of the story here is that in this regime, it's like picture A there. If the origin is connected far away, it's essentially because 1 or 2 balls brought it far away. You cannot have this conspiration of several balls trying to help you. If lambda is bigger than lambda c, then something similar should happen for the vacant. But here it's really exponential decay. We're rather surprised. So for the vacant, the fact that it can have very fat balls don't hurt you I mean, they work in the opposite direction. They actually kill this more. So. And when lambda is equal to lambda c, something very interesting happens. You cannot have A, you cannot have B. What do you guys expect, C or D?
Well, either C or A or B.
Either
C or
C, A, or B.
Or B maybe.
So what people would rule out more certainly is D, I guess. That's from what I heard. Yeah, indeed, C is correct. So although both C and D look pretty much conspirationist, yeah, C happens. It's very unstable. It only happens at one single point. It's not that surprising. But indeed, there are infinitely many circles of occupied and vacant paths surrounding the origin. They get bigger and bigger. That's why it's possible. I mean, very big, very fast, exponentially fast. And the probability that the origin is connected to some point, say in the vacant, is more or equal than x to the minus c. It's also bigger or equal than x to the minus c, so c prime. So there is indeed a polynomial behavior ruling the critical phase. That's what attracts us the most, is the critical phase, because there's these strange things happening, the polynomial behavior. There's some hope to explain this in the scaling limit. Yes?
So if O decays like, I don't know, the radius to the minus 3 and then some log correction to make this integral finite, somehow your bound here is already not polynomial.
Yeah. But that's why I wrote vacant here. Yeah, he's right that he could not violate star, so still have a plane that's not completely covered by balls, but have a decay of this type that's not even polynomial. It's like 1 over log. You can cook up these examples, so this could decay to 0 very, very slowly. That's why I wrote this as the vacant set, because this is not true for the occupied.
I think you should always converge to SLE and have the same.
Yeah, that's another point. You know, this would violate the SLE assumption. So SLE is what I was telling, that at criticality, you expect that you have some scaling invariance. You start to scale the model, like look it from further and further away, and you start to see some picture that is not non-degenerate, not becoming something completely occupied or something completely vacant, but there are bubbles of this type everywhere. Like these guys appear in every scale. So this was very successful undertaking for Bernoulli percolation, for the discretization of this lattice by some magic that only occurs in certain models. And would that happen also for this model? The problem is you need this polynomial decay, and it can be violated. But we still didn't settle for our belief. Sorry?
For the vacant, is there a reason why it's similar to?
Yeah, then you have the question. The vacant also has a problem because the vacant can connect. It has this, the vacant can be blocked with some reasonable probability, but it will fill the boundary of big balls. But if instead of looking at these events, we call these guys arm events, which should decay polynomially. If instead of looking at the arm events, you look at some, say, Cardis formula, then we don't have a conjecture. We believe it should be true, but we're too shy to conjecture anything. And to finish in the last 3 minutes I have, I just want to say a little bit about how we proved this. The technique is not completely unrelated to Roy's. It's he also uses some scaling arguments, but he also mixes with some other ingredients, which don't work here. But the idea is basically a renormalization scheme. So if you ask a physicist, everything I told you is trivial. It should happen. And the reason why is because they have this renormalization group picture in mind that explains everything. So if you take, say, a rectangle like this, and you look at the probability that you find the crossing, either vacant or occupied, you choose, at a certain scale. So there are two ways to do this. Either you increase this box, or you can fix the box like a continuum box and shrink the model. They prefer to think it as a shrink in the model. Doesn't matter. So this is a dynamical system evolution. In the space of all the possible models you can have for percolation, all the possible random media you have. It's a very nice space, very difficult to even write what it is, or to give a topology to this is a nightmare. It has been done, but it's very difficult. And you have this operation of shrinking it. So you have a model, shrink it, get another model. And that's a flow. So from this renormalization group perspective, there is this nice flow defined there, and there should be, this drawing I did is terrible for the actual flow that's taking place there. This is more of a nicer picture. So everything empty is a fixed point. If you don't have anything in your media, everything is vacant, and you shrink, you get everything vacant. So that's a fixed point. Everything occupied is also a fixed point. And, from these two fixed points, there should be something going on. And they believe there's an unstable manifold here with a fixed point and a stable manifold. And, if you start to follow the arguments, I find it very, very beautiful, very inspiring. I wish I could say anything about this. But it's not completely far from our argument. So we do consider this operation. We shrink the model and we give bounds which are working on these two regions. And then we try to grow these balls until they touch at the critical point. And this is already appearing, very strongly in Kasten's work. So what's the difference between what we've done and what Kasten did? Which is, how this whole thing started in probability was by Kasten's proof that this is true for the discrete work, for the discrete model. The big difference is that the argument to show that these two balls actually touch each other at the critical point. So the attractors for the supercritical phase and the attractor for the subcritical phase, they touch at a single point. And this argument is called Russo-Samuelsch, and it's a bit more robust. So that's the message that we're trying to convey, that people should massage more the Russo-Samuelsch, because I think it's connected to something that we should have any idea about how it works, and for now it's still very hopeless. I think it's a point to stop. Thank you.